Good evening, everyone. So welcome back to the Special Functions and Number Theory seminar. So our speaker for today is Professor Jehanne Dousse, and she'll be talking on Andrews-Gordon-Bressou type identities and particle motion. Over to you, Jehanne.
Thank you very much for the invitation to speak in this very nice online seminar. So I will talk to you today about some partition and Q-series identities, which are due to Andrews, Gordon, and Bressou. And the talk will focus on some bijective ways to obtain the sum sides of these identities. I will explain all of this. So so this will be quite combinatorial with bijections and things like that. And yes, so this is based on two papers. The first one is from last year with Frédéric Jouet and Isaac Conan, and the second one is from this summer with still Frédéric Jouet, but now Ji-Hyuk Jang. Okay, so oops, yes, it's working. Yeah, so let's start with by recalling the usual definitions. So integer partitions are simply non-increasing sequence of positive integers. And if those positive integers, which we call parts, sum to some integer n, then we say that it's a partition of n. And we also say that n is the weight of the partition lambda. And the number of parts is called the length of the partition. So, for example, here I wrote all the partitions of 5, so you can see them here. And partitions can be represented by Young diagrams. So, for example, this Young diagram here will be the partition 3, 1, 1, because you have 3 boxes in the first row, 1 box in the second row, and 1 box in the third row. Okay, so we will be here interested in generating functions of partitions, so we will need this notation, the Küppelshammer symbols they are called. So AQ sub n is a product for k equals 0 to n minus 1 of 1 minus AQ to the k. And n here can be either an integer or infinity. And we will have a lot of big products, so there is a shorter notation here. We can write A1, A2, etc., AM. That will be the product of the Küppelshammer symbols, A1 sub k, etc., up to AM sub k. And an important fact is that if you consider partitions which satisfy some congruence conditions, then you have infinite products as generating functions. So if you take partitions into parts congruent to some integer k modulo n, then you can write their generating function as 1 over qk, qn infinity. And also, some other facts that we will need later is that the generating function for partitions into at most k parts, or equivalently parts which are at most equal to k, is equal to 1 over qq sub k. Okay, so we will use that immediately by studying the Rogers-Ramanujan identities. So initially they were discovered in this shape, so Q-series identities. So yeah, actually their story is a bit interesting because it was first discovered and proved by Rogers at the end of the 19th century, but it went quite unnoticed at the time. And then later Ramanujan rediscovered them in 1914, initially without a proof, but then he found Rogers' work, and then together they found a simpler proof together, which they published in 1919. So these identities say that on one hand you have this sum, the sum of qn squared plus 1 minus a times n divided by q sub n, and this is equal to the infinite product here on the right. And in terms of partitions, it gives us a nice partition identity because on the right, because of what I said on the last slide, you can recognize partitions into parts congruent to 2 minus a or 3 plus a mod 5, which I wrote here in a slightly shorter way. And on the left, you have a generating function for partitions with difference at least 2, which comes from the qn squared here, which you can write as 1 plus 3 plus 5, etc., etc. So a staircase of even numbers, odd numbers, sorry. And so this has difference exactly 2. And to this, you will add some partition into at most n parts, which is generated by the denominator. So you get partitions with difference at least 2 after you do this. And here the A will decide whether the part 1 can appear or not. So you have two cases. And these identities are very important, both in combinatorics, but also in other fields, because it has been used in theoretical physics, number theory, representation theory, algebraic geometry, and possibly even many other fields. But these identities, they appear naturally in many, many different places. So they are very interesting for that. And they have been generalized combinatorially in the 1960s by Gordon, who said that there is again a partition identity between two sets of partitions. The first one, which I call TRK of n, is a set of partitions of n, where now you still have difference at least 2, but before, you remember, it was between consecutive parts, so it was the part lambda I minus lambda I plus 1, but here, now it becomes lambda I plus k. So you have difference 2, but at distance k, not distance 1. And also the part 1 has a restriction that it can appear at most k minus r times. And on the other hand, you have the set of partitions of n into parts which are not congruent to 0 or plus or minus k minus r plus 1 modulo 2k plus 3. And for all n, these two sets of partitions have the same cardinality. So this generalizes more the combinatorial version of McMahon that I just presented. But soon after, Andrews found also a Q-series version that generalizes the original form of the Rogers-Ramanujan identities. And those identities are called the Andrews-Gordon identities. So you can notice that similarly to before, you have a sum which is equal to a product, and the product corresponds to congruous conditions, and the sum corresponds to those difference conditions. But as we will see, this is not exactly obvious to see directly. So let's first see what is the natural interpretation of this sum. So here, we can rewrite this sum by using the Q binomial coefficients. So yeah, they are defined that way. They are a quotient of Q-Pochhammer symbols. And they are the generating function for partitions whose Young diagrams fit inside a k times n minus k box. So in other words, which has a largest part k and number of parts at most at most k, and number of parts at most n minus k. And if you want to rewrite this, it's just a small calculation, you can rewrite it using those Q binomial coefficients. And in that way, there is a more natural interpretation, a combinatorial interpretation, which was given by Andrews, and which is the following. So those, for example, this S1 squared, we will see that as a square in the Young diagram called the Durfee square. So that will be the first, this big square here. Then the QS1 here gives us a partition in here, which I call mu1, which is a partition into at most S1 parts. You put it here. Then the S2 squared, sorry, will give us another Durfee square here. And the partition mu2 will be here generated by this Q binomial coefficient, which is the generating function for partitions fitting inside a box of size S2 times S1 minus S2. So a partition that fits exactly here, etc., etc. And at the end, we had some plus sk minus r plus 1 plus sk. So for example, let's say, let's look at the last one. Let's say k is 4. So we end up with s4 squared plus s4. So the difference will be that we will put a square, but we will put also a single row below the square corresponding to this sk. And there is nothing to the right of the row, which I denoted here by these little crosses. And again, here the Q-binomial coefficients gives the partitions here that fit in those rectangles. Okay, so combinatorially, it is natural to think that the sum side of the Andrews-Gordon identities generate partitions which can be decomposed in this way. That is, which have sk successive Durfee squares or rectangles. Okay, but it is not obvious when you look at this sum that it is the generating function for the partitions in the set TRK defined by Gordon, which was the the partitions with difference at least 2 between parts at distance k. And the whole point of what I will explain today, so this bijection with particle motions, is actually to see that the sum side of the Andrews-Gordon identities is indeed the generating function for the set TRK. So originally, Andrews did not do it bijectively. He did it by showing that these sums, they satisfy some recurrences, and that the partitions in TRK also satisfy the same recurrences. So he proved it analytically in some sense. But Warner, in 1997, did it bijectively with the particle motion that I will describe today. Okay, so now I will explain to you the principle of this particle motion. So instead of seeing partitions as I defined them before, as a sequence of parts, we will actually see them as a frequency sequence. So we will see them as an infinite sequence of non-negative integers called fi, such that fi denotes the number of appearances of the part I in the partition lambda. So for example, if in the previous notation the partition was 6, 5, 5, 5, 3, 3, and then 4 ones, then in terms of frequency sequence, we will put a 4 first because there are 4 ones, then a 0 because there are no 2, then a 2 because there are 2 threes, then a 0 because there are no 4s, a 3 because there are 3 5s, and a 1 because there is 1 6, and then only zeros because there is no number larger than 6 in this partition. And to do the bijection, it will be convenient to visualize those frequency conditions as diagrams like this, where you put columns, and on the ith column you have fi boxes. Okay, so that's what we will use as a representation. So thankfully, the Andrews-Gordon identities can be reformulated nicely in terms of frequency sequences. So actually, the fact that you have a difference at least 2 at distance k is the same than saying that for all I, the sum of the frequencies of I and I plus 1 is at most k. So to just get an idea, if we take k equals 1, like in Rogers-Ramanujan, we had either that the difference between consecutive parts needed to be at least 2, or here we would get that the frequency of I plus the frequency of I plus 1 is at most 1. So if the frequency of I and the frequency of I plus 1 is at most 1, that means that you cannot have either 2 times the part I that appears, or both the part I and I plus 1. So in that case, that means that you forbid repeating parts and consecutive parts, so that means that parts differ by at least 2. So with general k, it's really the same idea, just tiny bit more complicated, but very similar. And we still need these conditions that the part one appears at most k minus r times. So this is very nicely written in terms of frequencies. It is equivalent. Okay, so what we will actually prove is that the sum side of the Andrews-Gordon identities is indeed the generating function for partitions whose frequency sequences satisfy these relations that I just highlighted. Okay, so yes, so Werner originally when he introduced his particle motion, what he proved was not exactly the Andrews-Gordon identities, but it was a refinement or a finite version actually of those identities. So he was considering the two conditions that I just mentioned, but also he added one last condition, which was that the parts are all smaller than some big L. Okay. And he showed that using particle motion that the generating function for these partitions is this big sum with again q binomial coefficients here. So the details of the binomial coefficient here are not extremely important, but the only thing you need to know is that when L, so the bound that he put on the largest part, tends to infinity, then those m's that are inside, they also tend to infinity. And if you have a q binomial coefficient and one of the, like either the number on top or bottom tend to, when the number, forget about the bottom, when the number on top tends to infinity, then what you get is 1 over QQ index the number in the bottom. So this would give us 1 over QQ Sj minus Sj plus 1, which is exactly what we get in the Andrews-Gordon identities. So this expression, when L tends to infinity, tends to the sum side of the Andrews-Gordon identities. Okay, so his idea was that first you consider this part of the generating function, and you say that we will find a partition which has exactly this weight and which satisfies the conditions, the frequency conditions of Andrews-Gordon. And then this part, the Q binomial product part, we will obtain by inserting those parts inside the minimal partition using the particle motions. I will show you exactly what it is. So that you get an idea, for the simplest case is when r equals 0. And so in that case, you don't have this sum here, you just have the sum of squares. And in that case, the minimal partition is very simple. It had a frequency sequence given as follows. So first you have sk times k0, 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 etc., etc. Then you have I0, 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 si minus si plus 1 times, etc. You end up with 1, 0, 1, 0, 1, 0, s1 minus s2 times, and then only zeros. So clearly this satisfies the conditions of Andrews-Gordon. And yeah, you can here see an example when k equals 4.
Jehanne?
Yes?
What's the definition of a minimal partition again? Sorry, I may have missed it.
So far there is no... so far the definition, if you want the definition of the minimal partition is just this. So it will be the smallest partition that satisfies that has this size and satisfies the conditions from the Andrews-Gordon partition.
Okay.
So here, in that case, this is for r equals 0, the definition is here.
Okay.
And when r is not 0, it's a tiny bit more complicated, but similar.
Okay.
Yeah, thank you. Yes. Okay, so just keep in mind that later we will start from this partition and apply some particle motions to it. But we don't know yet what particle motions are, but we will know in the next slide. Okay, so the definition of particle motion itself can, in theory, be applied to any frequency sequence. It doesn't need to be of the shape that I described before. So we just need to take some index, u, such that if you consider the sum of the frequencies of u and u plus 1, and if we call it h, then for all the numbers that are at least u, the sum of the frequencies, for all the numbers v that are at least u, the sum of the frequencies of v and v plus 1 must be at most h. So in that case, if u is such a number that satisfies this property, then we can apply particle motion to it. And there will be two cases. So the first one is when, okay, so first so h here on this example will be 5, okay? Because u will be this index here. So we have fu, which is 3, fu plus 1, which is 2. So h is 3 plus 2 equals 5. We can apply particle motion here because the next, well, it's a very small example, but then the next two frequencies are 2 and 1, which are at most 5, so we can apply it, it's no problem. So what we do is we check the next two frequencies and compute their sum. Here we just saw the sum was 3. And we see whether it's smaller than h or equal to h. So the first case is if it's smaller than h, then we can do the particle motion, which will consist in moving one box from the u column to the u plus 1 column. So here we obtain this partition. So in other terms, in terms of frequency sequences, it consists in transforming fu plus 1 into fu minus 1, fu plus 1 plus 1. Okay. And then if you do this, you just leave u unchanged. You stay here, and maybe you can apply it again later. In the other case, if the next two frequency sequences have a total value which is equal to h, which is the case in this example. So we have in total 5 boxes also in those two columns. Then actually you will not transform those two columns, but you will transform u into u plus 1. So instead of focusing on this pair of frequencies, you focus on the next pair of frequencies. And then later, when we will do particle motion, we will apply it many times in a row. So the idea is that more or less you will start by applying it as long as you can. And at some point you will have this condition which is satisfied. So then you will need to move to the consecutive pair of frequencies to apply it again. So here we have an example. So let's start here with this partition. So here, the h that we considered before, so the sum of this frequency and the next is 4. So we look at the next two frequencies, so their sum is 2, so we can do the particle motion. So this little box here will move here, so we get this. So now, okay, we want to apply it again. So now the sum of this and these frequencies is 3, which is still strictly less than 4. So again, we do a particle motion. Oh. This box moves here. Now, if we want to apply it again, we look at the sum of the next two frequencies, which is now 4. So where the sum of the next two frequencies is the same as the sum of these two frequencies. So we do not do a particle motion, but we do a focus shift. So instead of studying these two columns, we study these two columns. And here we can do particle motion because the...
Namaste.
Yes?
मीटिंग नहीं लेक्चर में है अच्छा आप कुछ
Krishnan, can you mute?
Oh, yeah, sure, sorry.
Yeah.
Okay, so you didn't have a question. No. Okay, so I continue. Yes, so yes, okay, so we shifted the focus from this pair to this pair. And here we can apply particle motion again, because now if you look at the next two columns, they have only 2 boxes, so we can apply it. So we get this. We can continue applying it again. And yes, here we have again the case where we will have a focus shift, because between these two columns we have 4 boxes, and between these two we also have 4 boxes. So we do this focus shift, and then we keep moving particles, etc., etc. And here, well, yeah, I did it 9 times, and at the end you get this partition. Okay. So this is just always the same process. And particle motions have a few interesting properties. So yes, I wanted to, first introduce a notation. So if you start from index u, like we did, and starting from this index you perform m particle motions, then we will denote by PMU of m of f the frequency sequence that we obtain. So the two properties that are important is that if you apply the particle motion once, you increase the size of the partition by 1 because you remove a part u and you add a part u plus 1. So the difference of the weight of the partition between those two will be 1. So if you apply m particle motion, you add m to the weight of the partition. Also, by definition of particle motion, if you have a frequency sequence that satisfies the frequency conditions of Andrews-Gordon, then after applying particle motions, it will still satisfy those frequency conditions. By definition, because if you have fu plus 1, which is h, and then on the right everything is at most h, the particle motion was made so that you still have, after applying it, the sum of frequencies of everything to the right of u that will be at most h. So if it satisfies the conditions of Andrews-Gordon, which was exactly of that shape, then it will still satisfy it after applying particle motions. Okay, so in Werner's formula, we said that the minimal partition that I mentioned before was coming from this, and this product of Q binomial coefficients was coming from the particle motion. So actually, we will not show exactly this result because for our purposes, we don't need the finite version of Werner, so we don't need the Q binomial coefficients. We just need the infinite version. So I will show you how to get Andrews-Gordon, but just in the general case and using our generalization. Okay, so let's do this now. Do you have any questions until now? No, I think, okay, whatever. So don't hesitate to interrupt if you do. Yes, so with my co-authors, we found a generalization of Werner's bijection, which comes from actually a very simple idea initially, which is to allow parts of size 0. Because in general, in partitions, you have only positive parts, so no zero parts. But actually, here we noticed that to do particle motion, it had a much more general field of applicability if you allow parts of size 0. We will see why in a few minutes. So let me slightly modify the definition of partitions. So instead of being non-increasing sequences of positive integers, so now it will be non-negative integers. And the frequency sequence, instead of starting at 1, will start at 0. So we will have also a certain number of appearances of the part 0 in the partition. Okay. And, well, yeah, this is just a relatively obvious remark, but the part 0, they do not contribute to the weight of the partition because they are equal to 0, but they will contribute to the length. So they count as parts, but do not contribute to the weight. Okay, so we will define. So here, basically, what we will define on this slide is something that we will call the frame sequence. So this will be similar to the minimal partition of Werner, but slightly different, of course, because now we take into account those parts 0. So again, the idea in the end will be to get the sum side of the Andrews-Gordon identities. So you remember in the Andrews-Gordon identities, in the denominator, you had a product of Q-Pochamer symbols, which correspond to a k-tuple of partitions. So we will consider, we will start with a k-tuple of partitions, and those partitions can be the empty partition or they can contain the part 0, that's not a problem. And we will try to insert those partitions inside the frame sequence that we will define to get the sum side of the Andrews-Gordon identities. Okay, so if you have a k-tuple of partitions, the size of this k-tuple will be the sum of the sizes of all the partitions inside. The length also is the sum of all the lengths. And we will define some integers, s1, sk, such that the length of the partition lambda I is si minus si plus 1, where we define, we chose the convention that sk plus 1 is 0. And if you have such a k-tuple of partition, the frame sequence associated to it is, we define it that way. It is very similar to what Warner did, but the difference is now we start with frequency 0. So already for Warner, I only gave you the particular case r equals 0, but in that particular case, it was really the same definition, except we offset all the indices by one lower. So we start at 0, and we do k0, 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 but yes, starting at 0, not at 1. And the rest is all the same. The only difference is that we start at 0. So, for example, if our k-tuple of partitions is this one, that is k equals 4, then we will do, so first we can compute those numbers. So we say that we want the last partition, so the partition lambda 4, to have length S4 minus S5, which we define to be 0, so S4 is 2. Then we want this partition to have length S3 minus S4, so therefore S3 has to be 6. This one is the empty partition, so S2 is equal to S3. And this one is a partition of length 2, so S1 is 8, which is 6 plus 2. Yes. So the frame sequence that we get from this is just the following. So we put 4 boxes in column 0, 0 boxes in column 1, 4 boxes in column 2, 0 boxes in column 3. So this is because we have first 2 pairs like that. Then we do 4 pairs 3 0 3 0 3 0, because we need S3 minus S4 pairs like that. Then we have 0 pairs 2 0 2 0, because S2 is equals to S3, and we have 2 pairs 1 0 1 0, because S1 minus S2 is 2. Okay. So there we go, we have our frame sequence. And now we will see how to insert those parts of the k-tuple of partition lambda inside the frame sequence. So let's see. To do this, we will, so this will be the bijection. So just let me just define some sets of partitions. So the bijection that we will define will be between pairs of k-tuple of partition lambda and their frame sequence, like we just saw on the previous slide, and between a set AK, which is the set of frequency sequences that satisfies the conditions of Andrews-Gordon here. So Fi plus 1 is at most k for all I. And but here we don't have any condition on the number of appearances of the part 1, like in Andrews-Gordon. And also, other small difference here, we still have parts 0, which we did not have in Andrew's Gordon. But don't worry, at the end of the proof, there will be the parts 0 will be useful exactly as we want, and we will get exactly the partitions of Andrew's Gordon. Sorry, 1 second. Yeah. It's unfortunately the fall here in Switzerland, so I have a cold. Yes. So, okay. The bijection that we will give will be a map lambda from pk to ak defined by starting with the frame sequence and applying successively particle motions, which will start at indices at even indices, and the number of particle motions that we will apply will be the parts of the partition in the k-tuple. So to simplify notation, initially the k-tuple of partitions was written like this. So you had a partition lambda 1, etc., a partition lambda k. Actually, we just all write them in a row and call these and name their parts lambda s1 minus 1, etc., up to lambda 0. And we will insert those parts by particle motion exactly in that order from left to right. We will see an example on the next slide, also I think at least. Yes. So we still keep the same example as before. So here on top I rewrote the k-tuple of partitions. And what we do is that we will first insert a 3, okay? Because it's just the first part here. So we will do 3 particle motions starting at the last index. So at index 14 here. So we do, I do not write the detail, but if we do 3 particle motion, actually when it's just one block and everything is empty on the right, you just move it to the right every time. So you get this after doing 3 particle motions. Then we will do 1 particle motion at index 12, because you have a 1 here. And so you get this partition. Then when you have an empty partition, then it doesn't count. It doesn't have any parts, so we just skip this empty partition. Then we try to insert the 6. So the 6, we will do 6 particle motions at index 10. And well, this is the result that we get at the end. So it could be that that the particles that you move, so you see here you had something around 13. It could be that if you have some big number here, the boxes here will go further than the next box that was there, but that's not a problem. It can be done. So this is what you get. So then you do 6 particle motions at index 8. You get this result. You do 5 particle motions at the next index. You get this. Then 3 particle motions here. Then, for example, here we have a very big number, so those boxes, they will move very far. But yeah, no problem. And sometimes if you have a part 0, which can happen too, well, that means you do 0 particle motion at some index, and that's also fine. So this stays as it is. So the final result is this. And as we said before, the advantage is that when you have some frequency conditions like that, we said that particle motion preserves it. That's what we said that on the previous slide. And in that case, so this was the condition of the Andrews-Gordon identities. The frame sequence that we started with also satisfies this condition. So when you apply however many particle motions, which was determined by the k-tuple of partitions lambda, what you get is something that satisfies this condition still. So it is indeed something that belongs to the set AK. The set AK was just a partition satisfying this. Okay, so we are in the right set. We said also, yes, so we were saying that when you do m particle motions, you increase the size of your partition by m, the weight. When I say weight or size, it's the same thing. Here, therefore, what we did is the partitions of the k-tuple lambda, we were doing if you add a part lambda I in this k-tuple of partition, then we were inserting them in the frame sequence by doing I particle motions. So when we were inserting the part lambda I in the frame sequence, we were increasing the size of the frame sequence by lambda I. So the total size is preserved. And so far, of course, I haven't proved that it's a bijection. I will actually not exactly prove it in detail here, but you can do it by defining some other procedure gamma, which is the inverse of lambda. So the steps are not too hard to describe because you can do the reverse of the steps of particle motion. But proving that they are actually inverses of each other and that you get a bijection rigorously takes some calculations that I will skip here. I hope you don't mind. And some interesting remark is that actually, if you want to find Warner's minimal partition, you can obtain it from our frame sequence by considering this very simple k-tuple of partitions. So if you apply lambda to this k-tuple of partitions and our frame sequence, what you get is the minimal partition of Warner. So basically from our approach, we can deduce the approach of Warner. The contrary is not true. But if we have some parts in this k-tuple which are smaller than the numbers you see here, we will get things that Warner could not get by not having the frequency 0, basically. Okay, so this bijection so far, as I said, is not between exactly the sets that we want. So it is between this set pk of pairs of k-tuples of partition and their frame sequences, and the set ak of partitions satisfying the frequency conditions. So because of our bijection, we have this identity. Now, let's see, because ak, we were saying, was exactly this. So we were saying that there are two differences from this to Andrews Gordon. It is that you don't have any condition on the appearances of the number 1, and also the frequency started at 0. So we will rewrite this slightly to get the sets that we had in Andrews Gordon. So first of all, we will add a bit arbitrarily a condition on the number of appearances of the part 0. So it can be anything between 0 and k because of this condition. And of course, if you add this condition to the set, you will get a disjoint union because of course if the part 0 appears r times, it will not appear another number of times. Okay, so you can write this disjoint union. And now actually this set, each of these sets in the disjoint union is in a very simple bijection with this set, where, oh, sorry, that's my bad. I wanted to do, here I should have put I at least 1, not 0. It's a typo, I'm sorry. So if the frequency of 0 is exactly r, and we know here that the frequency of 0 plus the frequency of 1 is at most k, then if you have this, that means that the frequency of 1 is at most k minus r. So the bijection, but I don't even want to call it that way because it's so simple between those two sets, is just to remove the parts 0. And you get, so again here it should be a 1. So you get a classical partition into positive parts where the part 1 appears at most k minus r times. So this set is exactly the set TRK, which was defined in the Andrews-Gordon identities. So AK is a disjoint union of sets TRK.
Jehanne, how do you get the second equality when you have the first time the union r equal to 0 to k?
Which equality?
Second equality.
So no, this equality?
No.
This?
For this? When you
this equality.
Yeah.
Yes. So okay. So because of this condition, we know that the part 0, or actually every part, can appear at most k times. Otherwise, this would be wrong already, okay? So in particular, the part 0 can appear at most k times. So it can. So here I just distinguish all the cases in terms of how many times the part 0 appears. So it appears. It can appear any number r between 0 and k times. So this is all I'm writing here. Yes. Thank you for the question.
Yeah.
Okay. So we have this disjoint union. Okay. So that's good. And by the Andrews-Gordon identities, we get that the sum of so here we had the sum of the generating function for the partitions in AK. Because of the disjoint union, we can write it as a sum of the generating functions of all the sets in the disjoint union, so all those TRKs. And by Andrews-Gordon, you know that the generating function of these TRKs, they are, yes, of the sum on one end, but also the product, if you assume that the Andrews-Gordon identities are true. So in that sense, we can get that the generating function for AK is this sum of infinite products. On the other hand, by the definition of PK, which was just like this pair of k-tuples of partitions, frame sequence, and by doing the particle motion, we were, no, actually, without even doing the particle motion, just by definition, we know that the generating function for PK is the following. So the numerator comes from the frame sequence, and the denominator comes from the k-tuple of partitions. And from the bijection, we get that these generating functions equals these generating functions, so that this sum is equal to this sum of products. So as a free consequence of our bijection, but using the Andrews-Gordon identities as an ingredient, that's important, we get this identity, which was due to Bressou, and which has a slightly similar shape to Andrews-Gordon, but yes, so here, as you can see, there are some minuses here, minus S1, etc., minus SK. So for example, if we did not consider those frequency zeros that we did, we wouldn't have been able to get anything with minuses here. Because the smallest you can get by considering frequency 1 and more is the thing where we forget this part and we just get the squares. But if you have some negatives, you really need the frequency 0. Okay, so I promise that I will tell you how to get Andrews-Gordon from that. So actually, we will see that, and we will see another applications or two. So the idea will be to take the same bijection lambda that we defined, but instead of considering the full sets AK and PK like we just did, which gives us the Bressou identity that we just saw on the last slide, what we will do is considering subsets of AK and PK on which the bijection lambda induces also a bijection. And then we will compute the generating function of the subset of PK using just the combinatorics of the pairs of the k tuple of partitions that we consider to compute the generating function. And thanks to the bijection, this will give also we will have a nice expression for the subset of AK in terms of sums of infinite products, for example. So that will give us the product side of the identities. So we will see. Yes. So to prove, yeah. So this is just what I was saying basically. So if you want to find identities, you can get you can use Andrews-Gordon to write subsets of AK as a sum of infinite products. Okay, so let's see some example. So we define some subset of PK, which will depend on some parameters, J, R, and K. And the idea is that it is a generating function for again pairs, where one element of the pair is a k-tuple of partitions, the other element is a frame sequence. And now the k-tuple of partitions, they will satisfy some additional conditions. So here the condition on the length is exactly the same as before, but this one is new. We say that each part in the partition lambda m must be at least equal to some particular value here that we give. This value was chosen so that it will work well to prove our identities. So we just add a minimal value of the parts, and that's it. And what we show is that the generating function for these partitions in this new set x, j, r, k is the following. So we will see quickly why. So the idea that we will use all the time is relatively simple. It is that the generating function for partitions that have L parts, so that all the parts are at least D, is the following. So the idea is simple. We start, this numerator here will just give us L parts all equal to D. And this denominator is a partition into at most L parts. So we start with having all the parts equal to D, and we add to them some arbitrary partition into at most L parts. So we get the partition into parts at least D. So this is just a simple combinatorial lemma. And for computing the generating function of partitions in the set x, j, r that we just defined, where the condition was that each part of lambda m is at least equal to that, we just use this lemma. And according to the value of m, we have different cases to treat. So if m is smaller than j, this condition doesn't mean anything because this integer is negative, so we just get partitions. Here, for example, we will get m minus, so here the parts will be, when m is in this range, the parts will be at least m minus j, so we just apply this lemma with d equals m minus j, and we'll get this, etc. You have another case here, but when you combine all of this, what you get is this product, sorry. And so we have a nice formula for this. Then what we showed with Frédéric Jouet and Isaac Conan was that the map lambda induces a bijection between x 0 rk, so one of those subsets that I just defined with some particular value of I, is in bijection with trk, that was exactly the partitions in Andrews Gordon. So that proves via this bijection of particle motion that indeed this series is a generating function for the frequency conditions of the Andrews-Gordon identities. Yes, so that was just this was as a reminder what the set is for I equals 0. And actually, the minimal partitions of Warner, because for Warner, Warner did it already for Andrews Gordon. So the minimal partitions of Warner correspond exactly to the minimal partitions that satisfy these difference conditions. So we get, in the case of Andrews Gordon, if we do this manipulation, we get back what Warner got. But we can also get some identities that Warner did not get. So for example, let's see this identity of Stanton, quite recent, which he proved not combinatorially at all. It was purely analytically. And as you can see here, again, we have some minuses in the power of Q. So again, here, this one, it would need to have the frequency 0 to be able to be proved. So this is a generalization, of Andrews Gordon. So if you plug j equals to 0 in this, you get Andrews Gordon. And also, it is a generalization of the identity of Bressou that we got directly from the bijection. You know, the bijection, we had this between pk and ak. So this bijection was giving us an identity of Bressou. So this identity is the case r equals 0 in this. So we can hope that because this identity generalizes two identities which we could prove using particle motion, that maybe we can do this too. And Stanton asked us that actually last year. And we showed with Frédéric Jouet and Jihyuk Jang that actually we can. And the idea you will see is relatively similar. It's just that you consider yet another subset of AK and PK. So it's on purpose that I defined this set XJRK a bit more generally than just for Andrews Gordon, because actually here, if we do it for general J, what we get is, again, using the same lemma as before, is this generating function, which is exactly the sum side of Stanton's identity. So actually what we need to see is with what this set XJRK is in bijection with this with the map lambda. So actually, it is in bijection with some set ZJRK, which again satisfies, it contains the conditions, the frequency conditions of Andrews Gordon, and it contains some additional condition here about the number of appearances of the frequency 0 that are allowed. So you have this additional condition, so you can show that this is in bijection, but we want to prove the Stanton identity, we want to relate it to Andrews Gordon, because to get the product side, we need Andrews Gordon as an ingredient. So actually, what we did was to find another bijection between this set Z and another set Y. And it was not a very big bijection, it's just a bijection that modifies the number of appearances of 0. So you add some part 0 in some cases. So it doesn't change the size of your partition because you only modify part 0. But it will make the connection nicer with Andrews Gordon. So the set Y is the following. So instead of having the previous condition on F0, we have a different one. So F0 has to be inside this set. And again, we can write this as a disjoint union of sets like before, where we have the conditions of Andrews Gordon and a prescribed value for the frequency 0. So this, again, we saw that we can express using Andrews Gordon. So we get that the generating function for the partitions in YSK is the following. Thanks to the disjoint union that I didn't write here, you can deduce a generating function for Y, JRK, which will be a sum of terms of this form. So we get this. And Y of JRK is in bijection with Z of JRK, so we have this equality. Z was in bijection with the set X JRK that I defined before, whose generating function was the sum side. So by combining these two bijections, we get that this sum is equal to the sum of infinite products. And the advantage, I will finish with this, is that we can also get similar things for the Bressou identity, which is the Bressou identity is similar to Andrews Gordon, but instead of having odd moduli, we have even moduli here. And basically, it's all the same conditions except for frequencies, except that we have an additional condition here, which is some parity condition on the frequencies. So actually, we can also prove using the same bijection that the sum side is indeed the generating function for URK here. And there was a similar identity by Stanton, which generalizes Bressou in the same way that the previous one generalizes Andrews Gordon. So this one we can also prove using a similar idea, the same bijection. And there was another theorem of Coursungo's, which had the same conditions as Bressou, but the opposite parity condition. So there is just a +1 here, that's the only difference. So using the same bijection, we found the first expression for those generating function as a sum. because it was he had shown in another way that the generating function is equal to the sum of products, but there was no expression for the sum, so we could find that. And we could find also something in the style of Stanton, but corresponding to the parity conditions of Kurzweil. So this more general identity. And yes, so as you can see, you can get many different identities by using this bijection. Oh yeah, sorry, I think I can skip that. It's just, I was saying that it's the same idea basically. And yeah. Yeah, just an open problem is that in the same paper of Stanton, he had another identity quite similar, but with a binomial coefficient here. Not Q binomial, but binomial. And this one we don't know how to prove using particle motion, but if someone in the audience is inspired and they have ideas, please let us know. And I will thank you very much for your attention.
Thank you very much, Jehanne, for a very nice talk.
You're welcome.
Are there any questions? So I had one question. I was
Yes.
actually going to ask you about the Bressou identity for even moduli, but you already had it in your talk.
Yes, sorry.
Much more general than that, like the Stanton's one. So which paper of Stanton is this from 2018?
It is. Wait. It's. Well, I'm ashamed. I should. Okay, give me just 2 seconds. Because I don't want to say a wrong title. That would be bad. It has. Yeah. Okay, 1 second. Let me tell you. I have it on my phone. I just have to open it. It is. Yeah, so it is called Binomial Andrews-Gordon-Bressou Identities.
Oh, okay.
Yes, so yeah, because he was, well, actually, I'm on the
There is
right
a
page.
binomial
That's good.
coefficient.
Yes, because this one, I think that's probably where the title comes from, because
Yeah.
those binomials were quite,
Yeah.
well, in some sense,
Unusual.
rare. Like
Yeah,
in most
right.
partition identities, or Q-series identities, sorry, you don't have so many classical binomial coefficients that appear. You have sometimes, yes, Q binomials, but this one. So I think he wanted to emphasize more maybe this identity. But he has both the binomial and non-binomial version, and they both generalize Andrews Gordon and Bressou.
Right, right, right. Yeah,
Yeah,
yeah. It's very nice. Yeah.
yeah, yeah.
Any other questions?